So today's topic, compressible gas dynamics. So this is a science that was really born basically in World War II. P-38 pilots would jump into a dive trying to jump onto a Japanese Zero, and they would start descending at about 500 miles an hour, and they noticed something weird started to happen. They tried to pull out of the dive, and they couldn't. And a bunch of them crashed. It was a bad thing. Okay? And we couldn't understand what was going on. We put drag brakes on the P-38. We did all kinds of stuff. But eventually, when we got into the wind tunnel, we discovered that shock waves and compressibility phenomena was happening around the control surfaces. So we really needed to understand it. So let's go through some of the math behind it. And I'm going to do a video, and I'll show you how Mach 2 below, because I have lots of time to play, and quite frankly, it's fun. And there you go. All right, let's get into it. So, you guys have probably all seen Bernoulli's equation in fluids, okay? And this is great. It works a lot of the time for low-speed stuff. Okay. The problem comes when you start going at about 3/10 to half the speed of sound. This starts to break down. Then you got to play by a different set of rules. Okay. So in order to calculate the speed of sound, we use the equation, the square root of kRT, where K is the ratio of specific heats, R is the ideal gas constant, and T is the absolute temperature. So for room temperature, a little over room temperature at 300 Kelvin, throw these numbers in, and you get a speed of sound that's about 347.2 meters a second, or 776 miles an hour. Now, notice, K is a constant. Okay, that's the ratios of the constant pressure specific heat divided by the constant volume specific of heat. R is the ideal gas constant. Both of those are constants. The only thing that's changing is T, temperature. Speed of sound is totally and only dependent on temperature, which never felt right to me, but it is absolutely true. So things like kinematic viscosity, density, pressure, none of it matters. As long as you're within the realms of playing with an ideal gas, only temperature matters for the speed of sound. So implicit in that is when you're in nice warm air down here at the ground, the speed of sound is pretty fast. You go up high, 35,000 feet where it's 65 below zero Fahrenheit, your speed of sound slows down. So you're going to hear the term Mach number a bunch. You guys heard that in your other classes? Does that mean anything to anybody? I got one yes, two yes, okay. So Mach number, it's the ratio of object speed to the local speed of sound. So, commercial passenger jet, they typically fly at 0.80 Mach, and there's a good reason for that. 35,000 feet where the air is minus 54 C or 65 F below. What's the speed of sound at that temperature? Okay? Shake and bake the numbers. 296.8 meters a second. Or so that's the speed of sound. Then to get the object's velocity, we're going to take the local speed of sound times the Mach number. So 296.8 meters a second times 0.8. Object's velocity is 237.4 meters a second, or 531 miles an hour. not go as fast up high because of the speed of sound. But at 35,000 feet, you've got about 90% of the atmosphere below you. There's a lot less drag on the aircraft. For an F-16 cruising at 40,000 feet, I showed that video before. It's got the Pratt & Whitney 229 engine in it generally. You know, you got 29,000 pounds of thrust on that engine. You get to 40,000 feet, that same 229 engine only gives you about 6,000 pounds of thrust. But because the air is so much thinner, you can still go Mach 1.6 with only about 6,000 pounds of thrust. And another critical idea. Okay. When you are at Mach 1, when you are at the speed of sound, that is the speed of a disturbance propagating through air. Okay? So, if I have a bunch of really annoying honky-tonk, you know, steel guitar kind of music that doesn't work for me, and it's playing over here, if I've got a Mach 1 flow right in here, I can't hear it. It's silent over here. Other than the sound of a whole lot of rushing air moving really, really fast. Okay? None of that sound disturbance is getting through here. And that has some unique implications. So for example, you cannot burn fuel over Mach 1 in a conventional jet engine. Okay? The flame run simply cannot propagate through that Mach 1. Can't do it. Can't get there. Okay? Yes, we have scramjet technology. Yes, that's weird, ethereal stuff. If you guys want to go work on the Wave Rider, hey, knock yourself out. You can try to keep a candle lit in a hurricane. That's a very, very difficult combustion problem. Okay, so for a single, okay, and I screwed this up getting ready for this class. I gotta tell you, just about everything I did getting ready for this lecture, I screwed up at least 3 times. Okay, so I want you guys to know what I did wrong, so you do not do it wrong. Okay, so we got sonic choke flow, Mach 1, right there at the narrowest point. That means that for a single given upstream pressure, the flow rate at a Mach 1 orifice will not change regardless of how much the back pressure is decreased. Okay, so for exactly 1 pressure, 1, okay, you go to Mach 1, no matter how much I lower this back pressure, not going to change the flow rate. If I change the upstream pressure, if I pressurize this, yes, I can get more stuff to flow through there. Absolutely. And I totally screwed that up getting ready for this lecture. I was thinking, oh, okay, I'll have choke flow Mach 1. I'll raise the pressure, and the flow rate shouldn't change. That was utterly wrong. Huge wrong. Okay? And depending on how the class goes, I decided to make a little gizmo where we will actually look at that. So I have a flow meter here to measure the mass flow rate. I've got an orifice right here in the middle. So we're going to make the air go Mach 1 right at that little opening. We got 2 pressure gauges so I can see the upstream and downstream. And this thing is called an eductor. And that's providing vacuum from compressed air. And the way it does it, I take my compressed air, I bring it in, it mixes with the air in here, it comes shooting out the bell at the end, and because it mixes, it drags a bunch of other air in with it. Okay? So it's strictly a conservation of momentum device, but this is how you take compressed air and you can actually make very near a vacuum. Now, as I increase the mass flow rate into the eductor, my downstream pressure will go down. I have no control over the pressure up here. Okay, that's just open to atmosphere. So what happens, as I start increasing the vacuum, what you're going to see is that the mass flow rate will go up, 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 up. That's going to flatten out. Okay. When you hit Mach 1, right in this narrowest opening right here, it's going to become sonically choked. And then you'll be right here. And you will not flow anymore unless you do something to the upstream pressure. So if we get far enough, we'll do a demo lab over in Ferlin. Obviously, I don't have compressed air here, so I can't play with toys here in class. Plus, it's rather loud. They can probably hear next door. So we'll probably do a demo lab with that and actually show you that, yes, this in fact is a thing. So again, just remember, for exactly what upstream pressure. If I raise the upstream pressure and then try pulling the vacuum on the back, if I've got enough capacity, yeah, I'll have a second curve. It will be very similar, but it will end up at a higher mass flow rate. And I'm still flowing Mach 1, okay? I'm just flowing at a higher density. Still Mach 1. Okay, so the pressure I need to create Mach 1, right there at the narrowest part, can be calculated by this cool equation. So P exit over P inlet, ratio of the inlet to the outlet pressure, critical, meaning at Mach 1 equals 2 over K plus 1 to the K minus 1, where K is a ratio of specific heats. All right. All this jazz over here is a constant. So what we can do is do a little substitution since we normally play with air. And you come up with P exit over P inlet equals 0.528. So in other words, if I take this little gizmo and I've got 14.7 psi atmospheric pressure on this side, if I drop this side to roughly 7 psi, I'm at Mach 1, right in that opening. I always thought that was pretty snazzy, that it worked that clean. So of course, I had to go try it. I built something called a Schlerin optical system, and it allows us to look at flows by shooting a light beam through an object or a flow, and then the light gets bent according to the density of the flow. Sorry, guys. Okay, so I'm bringing the air up. So all I need is about 14.7 psi roughly, 10 psi. Just start watching right in here. See those ripples starting? That's right about 15 psi of inlet pressure, 20 psi. these are actually called oblique shocks. They're shock waves that form in the flow. And if we actually do that demonstration, I'll try to do this one for you as well. Okay, now notice, this is a very simple, straight nozzle type. We'll look at a cooler one in a minute. Let's talk about stagnation, pressure, and temperature. Remember when I showed you the clip from Top Gun Maverick, I said, yeah, why don't we calculate what that windshield temperature was? Yeah, we're going to do that. Okay, so stagnation pressure, also known as total pressure. Stagnation pressure, also known as total pressure, and temperature are the temperature and pressure that would result if we brought a flow to a stop adiabatically and isentropically. Okay. So the first one should look pretty familiar to you guys. Okay, the stagnation pressure stuff, that's all just Peto tube equation. That's where you're going to use this one. This one might be a little more nuanced. But that would be the temperature that's appearing at the end of that Peto tube. Okay, so Mav's dark star is cruising along at Mach 10. Some air molecules are being brought to rest against the windshield. What's the air temperature? Assuming Mav is at 80,000 feet, standard Blackbird flight altitude, and the air is minus 62 F or minus 51 C, which is the standard temperature for 80,000 feet. Okay, we'll start off, we'll calculate the speed of sound. So speed of sound comes out 298.8 meters per second. If a Mav is moving Mach 10, not Mach 1, so you're doing just a tad under 3,000 meters a second. I'm going to throw that into the stagnation temperature equation. And I realize that the stagnation temperature is now 4,664 Kelvin, or 4,091 C, or 7,935 F. Okay. Houston, we have a problem. So the melting point of fused quartz, which is the highest temperature clear substance that I know of, maybe sapphire is a little bit higher. Okay. That's going to melt around 2,930 F. So Mav's got a sunroof long before he ever hits Mach 10. Okay, it's going to get a bit breezy in that cockpit. Not to mention really stinking hot. So if you ever see these pictures of the SR-72 Dark Star and it's got a windshield, wrong. So you might be asking yourself, well, okay, the space shuttle came in at Mach 25. How the heck did it do that? Well, number one, they didn't come straight in. They didn't have the windshield pointed at the airflow. They came in at a 45-degree angle, and they put the heat shield on it, and they let the ablative tiles just vaporize and keep the airframe cool by vaporizing the tiles. So that may be how Mav is actually going to do it. Maybe he's got a little video camera and the windshield's not really a windshield. Okay? So back in the Bernoulli days, before compressibility, a nozzle looked like that. You got slow flow coming in, area goes down, faster flow comes out. Cool. When we start talking compressibility and going fast, it totally reverses. Now that we're going faster, we could have a fast flow coming into what is now a diffuser. And we've got a slower flow going out, but at a higher density. how we make supersonic nozzles, folks, which is hugely important in the steam turbine industry. So what we'll do is we'll have some flow coming in, it'll be subsonic. We'll hit Mach 1 in our throat, and if we have a low enough back pressure in the back end, we will come out supersonic. And you can actually calculate the Mach number with that equation. This felt a little bit unsatisfying to me because we got to use the upstream total pressure or stagnation pressure, which means you got to know the input velocity going into the nozzle, and that's not always known. So I may do a compressible gas part 2. We've got 2 lectures that I didn't put anything just in case of snow days. So we may do a little bit more with compressible nozzles, CD nozzles. So of course, I had to go build one. So here's the CD nozzle. It's got a narrowest point here. The area right here is twice this area. So this is if you do the math, this is a Mach 2 nozzle. Now I want you to watch right over here. Something interesting happens. See what just happened? Let me replay that. That's actually an important idea. So if you do not have enough exit vacuum, okay, you don't get a fully developed flow coming out the end. Once I hit the proper design point and I have enough pressure ratio, then it actually pops in and you get full flow through the whole nozzle. And again, you see the cool oblique shock waves forming coming out of the nozzle. This thing is going to give a much faster flow rate than that straight nozzle do. So this idea of the converging, diverging nozzle, that's a rocket nozzle. We also put them on the back of high-performance aircraft, like the F-35. It can do that same thing because it can develop enough pressure ratio. So by doing the converging, diverging, and sending the flow supersonic, we can get more impulse, more velocity, and that will raise your thrust by about 10% as opposed to just coming out straight. All right, that's it, guys. So no labs next week. Next one we're going to do is going to be some stuff on heat pumps. We'll do a cool, healthy, cooler lab, and you guys will be back with the coefficient of performance of a solid state heat pump. But I will go over all that in lecture next week. So, have a great short week next week, and I will see you then.